The symbolic package in MATLAB is extremely useful in coming up with expressions for error propagation, especially when we have something complicated enough to use the general error formula. So let's do that. Let's start a new script. Let's get started. Begin with a clear statement to clear all the variables and clearing the screen. And then we'll, since we're going to be doing symbolic variables, we should say what they are. So for the example given in the error propagation handout, we're calculating the area of an object and then the uncertainty in the area of the object. So we're going to have area, and just call it area, and then we have uncertainty in the area, and then we've got our x, our uncertainty in x, our y, our uncertainty in y, and those are our symbolic variables. Okay, great. So now we have to tell the script how we calculated the function of interest, and that was area. So we said the area was equal to x times y. Okay, and we also need to tell the script how to calculate the uncertainty in that area. Okay, so area is going to be the uncertainty in the area. We're just going to use the general error formula. So it's a square root. And then we just put in the uncertainty in every variable. So we'll do the uncertainty in x. And that's squared. And then the partial derivative says how rapidly the function of interest, in this case area, varies with the variable that we're talking about, x. So let's think about this for a second to make sure we understand why this makes sense. So this says how rapidly area varies with x. This says how uncertain x is. And both those contribute to how much x, or rather the uncertainty in x, is affecting the uncertainty in area. How uncertain x is, of course, but also how rapidly area varies with x. Because if area didn't vary with x at all, then the fact that x was uncertain wouldn't affect the area of A. So this just weighs how important this uncertainty is. And we have to write a function like this, or a term like this, for every variable. So it's easiest just to copy and paste, and then switch out the variables. So we've also got y and y here. So however many variables you have in your problem that contribute to area, you're going to have a term. So if there's temperature and mass, volumes, anything that has uncertainty is going to have a term in there. Okay, and to know how many variables you are, you just look one line above and see how many variables went into your function there. Okay, great. So we put in the general error formula, and let's just put a line of code in here that this was the general error formula. So the general form will be the same, but of course the details of which variables you talk about will be different for every situation. Okay, so at this point we want to actually get some numbers. So we have to put in the numbers that we're going to substitute into area. Okay, so for area there's two variables we have to substitute in. So we're going to put into x and y the new variables, or the new values rather, 15 and 30.4. So we'll go ahead and run the script, and we can see that it plugged in the numbers and we get this. And this is probably not what we were looking for. Usually we're looking for a decimal approximation, but we didn't tell MATLAB that's what we wanted, so it gave us the accurate answer. So if we want a decimal approximation, we have to tell it that. So we can do that by using the double command. So let's go back up to our script, and we'll alter this to say we're going to substitute the numbers in. So our x and y will be 15 and 30, and we're going to substitute that into x and y and calculate the area. But then we're going to take a double precision approximation of the actual number. So let's run the script again, and we can see that the number is 471.2. Great. We also need to do the same thing for finding the uncertainty in the area. So let's imagine that we wanted to find the uncertainty in the area, so we're going to do the same sort of substitution and decimal approximation, but the uncertainty in the area. So to do that, we would have to know the uncertainty in the x measurement, so we'll call that EX, and the uncertainty in the y measurement, we'll call that EY. And let's go ahead and plug those numbers in. Okay, so imagine that we had a rectangle that was an x measurement of 15.5 and a y measurement of 30.4, and the uncertainties on those two numbers, the uncertainty in x and the uncertainty in y, were given by 0.4 and 0.6. So we got 15.5 plus or minus 0.4 and 30.4 plus or minus 0.6. What would be the uncertainty in the overall area? So we run this one, and so now in the final version of the script, we have the number itself, and then we have the uncertainty. Now when we report these numbers, typically we're going to round this to 1 or 2 sig figs, and you should talk to your instructor to see what they want. In my classes, I want this rounded to 2 sig figs so I can see if it was calculated correctly. So this will be rounded to 15. And if this is rounded to 15, that means the last number on our uncertainty is that 5, which is in the ones place. So the last number we keep up here is the 1. So we have 471 plus or minus 15. So we keep the decimal place on the answer that corresponds to the last decimal place on our uncertainty. So the final answer would be the area of the rectangle is 471 plus or minus 15. So there's your example of using MATLAB to do the general error formula to determine uncertainty.